All right, welcome to CS3510. What is this, L10A, I think? The topic of today is something called chain matrix multiplication. We are going to focus on one specific dynamic programming problem that has a non-trivial solution, but note that it really encompasses a class, an entire group of techniques called, I don't know, partition DP. This is one of those techniques that I think is pretty rare to apply. And in fact, when we come up with exam problems and homework problems and so on, there's only like 5 problems we can think of max that apply such a technique. But it's one of those things that when you apply the problem, it's the only thing that works. It's like the only thing that makes sense. So we're concerned, it's called chain matrix multiplication, but we're not concerned at all with matrix multiplication. We talked previously about the runtime of matrix multiplication. This is actually a question about associativity. So recall associativity is, for let's say for multiplication of numbers, we have A, B, C, or we could say A, B, C, right? One of those is the correct way to, both of those are correct. Both of those will give you the same answer. And with respect to numbers, it doesn't matter what order you multiply them in. However, if these were matrices, it actually does matter because you can multiply rectangular matrices by each other, and they give vastly different costs depending on what order you multiply the matrices in. That's basically what chain matrix multiplication is. So suppose we had the following 4 matrices. Suppose we had a matrix A, which was, let's say, what is this? A is going to be, let's say, 50 by 20, and then let's say B was 20 by 1. And then C was 1 by 10. And then D was a 10 by 100. Right? And let's suppose we're not actually given the matrices. We're simply given the dimensions of the matrices. And we may say the dimensions of A are going to be 50 by 20. The dimensions of B are going to be 20 by 10. We'll write it this way. The dimensions of C are going to be 20 by 1. The dimensions of C are going to be 1 by 10, and the dimensions of D are going to be 10 by 100, right? So we may use this notation to say matrix A has dimension this times this when we write the numbers like this. Again, note that you can only multiply matrices if the number of rows of this one is equal to the number of columns of this one, right? So 20 is the number of columns, right? And 20 is also the number of rows. And recall, you do a matrix multiplication, you take it, and you flip it, and then you product it, right? You do that down. Now, because these share these dimensions, we can product these together. And let's suppose we want to compute A, B, C, D, right? We don't actually want to compute, we want someone else to compute A, B, C, D, but we don't want to compute the actual matrix multiplication. We just want to compute the most efficient way to compute A, B, C, D. And there are several associations. For example, it is the case where we could do A, B first, then do C, and then do the product of that with D, right? That's a normal way to do it. But it's also the case that we could have done C and D first, and then take the product of that with B, and then take the product of that with A. Pop quiz, if we multiply A and B, what is the output dimension of the matrix?
50 by 1.
Yeah, it's going to be 50 by 1, right? If you multiply A and B, which is a 50 by 20 and a 20 by 1, you're going to end up with a 50 by 1. So in fact, when you multiply A and B, it'll have the right dimension be 1, and guess what C has? Its left dimension be 1. So you can still multiply AB times C, and so on, right? True for any such association. These are not the only associations. You can also do right? You could do A times B, and then you could do C times D, and then you can multiply those two together. What else could you do? Is there any others? There should be more. Someone think of some.
BC.
Yeah, you could do BC, then you could do A, and then you could do D. You could also do BC, and then do D, and then do A. Are there any others? 5 sounds right. Can we think of any others? Okay. So first idea, bad idea. By the way, why must matrix multiplication and in general any association be operated in a binary sense, right? Why is it the case we don't have to consider the product of three matrices, something like this? This is an open-ended question. But why, if we multiply three objects, we must do so in a way that multiplies two first and then the third? I don't know if anyone has an answer to this, but do you know a way to multiply three numbers in a way that can be done without first choosing two to multiply first? I'll tell you a story. I was in, this was before I could read, I was in kindergarten, and they were teaching us arithmetic, right? So at first she tells us, okay, 1 plus 2, and I nail it. The next day, she says, okay, well, let's do something harder. Let's do 1 plus 2 plus 3. She's like, well, okay, write this down. And I misunderstood the question because I didn't know how to read, so I tried really, really hard to figure out a way to add three numbers. I knew you could add three numbers by adding two and then the third, but I didn't think that's what she meant. So I concentrated and I squinted really hard and I tried to add three numbers at the same time. Try it for a second and add three numbers at the same time. You can't do it. You have to choose. Every operation is binary. There's no such thing as a trinary operation that can't be done as a composition of binary operations, right? Multiplication is only binary. So you have to perform the association in some way. You have to either do 1 plus 2 first and then do 3, or you have to do 1 plus the sum of 2 plus 3. You have to choose one of those in order to add three numbers, so we need to solve the problem in a way that's left and right. There is no necessarily a choice of middle, okay? First thing to note. Questions on that? Okay. Second thing to note, let's suppose we were trying to find let's estimate the cost of matrix multiplication, right? I claim, depending on the association you have, there is a different number of operations that it takes to perform such a multiplication. And the order of multiplication matters. The association does matter. We want to first create a cost function of multiplying two matrices together that can just give us a ballpark estimate. We don't need a very precise cost function. We just need one that is good enough because we're going to be comparing cost functions to other cost functions, right? So what was the actual runtime of matrix multiplication? Does anyone remember? We didn't actually do, I don't think we did it, but we talked about, no, we did do matrix multiplication. Does anyone remember the runtime of matrix multiplication? Any upper bound? Yeah. Okay, well, no. Yeah, n cubed, and what was the algorithm?
Going in order of
Yeah, it was like Gaussian elimination, right? This was of an n by n times an n by n, right? So it took n cubed approximately. We did do faster than this. Did anyone remember? Strasson's, right? It was like 2.81, something like this, and then we mentioned you can get to 2.31 through writing 70-page papers and figuring out some really advanced stuff. But who cares? This is a good enough ballpark. Let's just say it's about n cubed. So multiplying two n by n matrices is about n cubed time, okay? But suppose we don't have two n by n matrices. That's too simple. Square matrices are too simple. Suppose we have matrix A and matrix B, and matrix A's dimension, let's say D0 and D1, and matrix B's dimension D1 and D2. What is a good cost measure of the runtime it should take to multiply A by B? First off, AB will have what dimension?
D0,
Yeah, D0, D2. So it'll take it'll have D0 times D2 entries. So it'll take us at least D0 times D2 entries to fill up, yes?
D0, D1, D2.
Yes, that's going to be our cost function. The cost to multiply AB should be D0, D1, D2. That makes the most sense in the terms of the operations we're going to have to compute. Now again, we don't need a very accurate cost function. We just need to compare costs. So we just choose a cost function that's got some sane properties. It sounds right. It's monotonic, for example. That there's, I mean, like, we all know big O hides constants, but forget about that for a second, right? Let's suppose we're, in a concrete sense, what is the number of additions and multiplications that needs to compute such a product? If you speed up the matrix multiplication algorithm itself, the cost function would speed up, but it would speed up for all matrices. So let's not even, it doesn't really matter. We just want to use this to compare. So some matrices, the product would still be slower than others because they have different dimensions. If this is the cost function that we want to do. So given these specific matrices, let's just kind of ballpark what the cost is of doing some of the products. So I will choose to do, let's do this one, and this one. So let's just choose to do those 3 products. And let's estimate the association. Suppose we first are computing B times C, and then we're going to multiply that with D, and then we're going to multiply that with A, okay? So first we're going to multiply B times C. So B times C has, B is dimension 20 times 1. By the way, there's lots of little numbers. Please make sure I'm not going to make a mistake on multiplication of simple numbers. But 20 by 1, and C is 1 by 10. So what should the cost of computing B times C be? Which is what? 200, okay. And this is BC, right? Plus, we want to compute BC times D. Now, BC has dimension 20 by 10. D has dimension 10 by 100. So what is BCD? Which is what?
20,000.
20,000, okay. It takes about 20,000 operations to go from BC to BCD. And now we want to compute ABCD, right? So we take BCD, which has dimension 20 by 100, and we multiply it by A. And what will A is 50 by 20. So what will be the number of operations to do that final multiplication?
10,000.
Yeah.
Should be 100,000.
Yes. Okay, so that's 120,200. Okay. Let's do a different association. Suppose we did BC, but then we did A first, and then we did D. We know BC is already 200. And then let's say we did A next. What will that be? It'll be a 50 by 20 times a 20 by 10. So 50, 20, 10 is what?
1,000.
Yeah, that sounds right. Okay. And what's the, let's do ABC and then multiply that by D. So we have a 50 by 10 times a 10 by 100. What should that give us?
50,000.
And that is going to give us 60,200, right? So first off, already we see that just doing A versus D at the last choice halves the number of operations. They're not even close to equal. And let's do the final one. Let's say AB first, and then let's do CD first. And then we multiply those together. What is the cost of AB?
1,000.
20 by 50 by 20 by 1. What's the cost of CD?
1,000.
So 1,000.
And what's the cost of ABCD? $50 by 1 and 1 by 100.
5,000.
Yes, thank you. So that's 7,000. Significantly less, right? So the order, there are always the same number of multiplications, but not each multiplication is the same because depending on which order you do the multiplications in, you can see that the number of operations required can vary wildly. 7,000 is incredibly small in contrast to 120,000, right? You would rather have 7,000 things than 120,000 things if we're trying to minimize something, right? So choosing the multiplication in the right order is important. Now, we also don't know that the other ones I didn't do are smaller, but I'm not too lazy to work it out. You can believe me that I have found for this specific set of matrices, I will tell you that AB and then CD and then the product of those two is the least one. Now, let's suppose we wanted a brute force search solution to this. We would check all possible parentheticalizations. How many are there? This is a combinatorics question. I don't know if we've seen this. The number of parentheticalizations corresponds to the number of ways you could put parentheses in a balanced form. Right. So for example, those are 3 examples of length 6 parentheses, right? 6 parentheses. How many ways are there to do so? Does anyone know? Yeah. Yeah, it is in fact the Catalan number. Why each parenthesis can actually correspond to a path in a lattice that does not cross the middle. This one, for example, would be open, 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 close, close, close. This one would be open, open, close, open, close, close. This one would be open, open, close, close, open, close, right? And if I were to rotate that, that's a path through the lattice that does not cross the diagonal, as long as they're all correct. So in fact, the number of such correct parentheticalizations is approximately the number of strings that are of this form, which is approximately the Catalan numbers, which is the number of lattice paths that don't cross the diagonal in a square. Now, how many of those are there? This for n matrices, this is approximately the Catalan number. Might be off by 1 or something somewhere. But does anyone know the cardinality of the Catalan number as a function of n? Nope, that's okay. Not expected to. It's at least like 4 to the n over n to the 3 halves. Okay. Don't really care to say anything more precise than that, but that's big and that's ugly and that's not good and that's bad, right? So first, all I'm saying here is that brute force searching over the number of parentheticalizations is quite bad. So brute force search is not going to work. We need somehow to find, and of course because we're in the unit, we're going to use dynamic programming to find something like an optimal substructure. We're going to find some way to represent the problem recursively and then solve smaller problems using dynamic programming. Before we explain that optimal substructure, are there any questions about the problem we're solving? Yes?
Yeah, I noticed with those parentheticalizations, the second and the third one actually represent the same order of multiplications.
Yes. Well, the second and third?
Yeah. They're both they're both equivalent to the last one we solved.
Right. But that's why I also said kind of like maybe, right? Because suppose I did insert the characters there. They're approximately still that. Right? Yeah. Yes. These, if you just remove the strings, if you remove the symbols, these two are the same sequence of parentheses, but they are different in the association because of the way the A goes here or it goes here, right?
Yeah.
So it's still approximately the Catalan numbers. Any questions, again, on the problem? Again, we're not given input, the matrices. We're not given the matrices. We're given only the dimension of the matrices, and we seek the correct association that minimizes the number of operations. Right? So what really is an association, and what is this problem we're solving? Immediately notice that, like, okay, part of an association is also an association, right? If you look inside a string of parentheses, you're going to find more parentheses. So maybe the problem is such that, like, you solve a small association, then you consider the next matrix, and then that's the next association. That's actually not quite it, and that's actually the difference between what we're learning today and what would be a more naive algorithm for dynamic programming. Because it is not necessarily true that given an optimal solution, its subproblem is also optimal. For example, suppose we know that the optimal for ABCD is to do AB first, then CD first, and then do the product of those. But what does that tell us about the optimal solution of just ABC? It doesn't tell us that the optimal way is to do AB and then do C, because C doesn't go to AB. C goes to D, which is not there. So we can't do it in a prefix way where we consider the next matrix as a function of the smaller matrices. We have to do something a little more creative, and it's going to be closer to considering all possible smaller associations. Another way to think about an association is like a binary tree. So if we have this association, this is analogous to a tree looking like this. And if we have the next tree, it's analogous to it looking like this. How am I going to draw this? Right? And the other one would be analogous to, we do A at the top level. Right? Those are three binary trees that correspond perfectly to the association of the way matrices are multiplied, right? Here you would do BC, and then you do the product of BC with D, and then you do the product of that with A. And that'll tell you exactly how to associate it. So for each of these three, for example, correspond these three binary trees. So really this is actually a problem on, maybe we won't even call them binary trees because the structure's a little different, but these kinds of trees. Now important to note though is that of a tree, like such a tree is constructed, it is a combination of smaller trees, right? So for example, this is some other small optimal tree, and so is this, right? So somehow we want to make connections between things according to, it's going to include our cost function, but the way we can choose the association, right? That's the next thing we're going to do. Questions on that? But again, it doesn't have this like monotonic property where like you can create a small one and the next one is a small one and the next one is a small one, because we know this is optimal, but this is not a tree for ABC. It has to be one of those two, right? All right, so let's talk, with DP it's always a good idea to rewind. Think about, in terms of recursiveness, what's the last thing you could do? The very last step you could always make. And so the last thing we're going to do is sum product. We're going to multiply some matrices. So if we have, what are our choices that we could make? And again, for DP, you always want to take a max, a min, or a sum, or a product, or whatever, an and or an or, some function over all possible choices. So let's just consider the last choice. If we have matrices, let's say A1 to AN, we have a few choices we can make, choose the last product, right? We could choose A1 to be last, and then A2 to AN. If that's our last choice, then what that means is that A2 to AN is some product that is handled as a smaller problem through the recurrence, right? But it's not necessarily true that that needs to be the case. So we would also have to consider, for example, A1, A2, A3, AN, right? We would also have to consider A1, A2, A3, AN. And then we would consider all of those, including A1 to AN minus 1. I'll draw it over here. AN, right? So the number of problems at the top level you have to consider is wherever you can put this open, this close open. Which do you split it for, right? So what it's going to be, it's going to look like this. Right? Wherever you could put that last multiplication is what needs to be considered. So what you would do is actually take the min of all of these. Does that make sense? Let the dimension of our DP table be DP of I comma j to mean min cost to compute AI to AJ, right? We want to compute, in good practice, we assign an English sentence to DP of IJ, so whenever we call upon DP with perhaps different letters than I and J, then we know exactly what that's supposed to mean, right? So what do we want we want to take the min of all of these options, right? But we need to compute the cost of each of these options, right? So we could say that DP of I comma j is equal exactly to what? What's the first thing we should think about? Pattern matching wise, monkey brain, not too much in-depth knowledge. First thing we should think that DP of IJ is?
You look at the sizes of the resulting matrix.
That'll end up being handled for us. But I'm looking for a simpler answer. Yeah.
So that would, you would just take that for the sub. Hold on. What?
It's tricky. It's tricky. Let's break it down. I guess what I'm asking is, like, we want to minimize something, so we will take a min. We know it's a min. We know it's not a max. We know it's not a sum. Remember, sum counts number of ways. You can check possibilities with ands and ors of booleans, but we know this stores positive integers, so we're going to do that, and then we're going to take the min over some kind of problem. Yes?
Yeah, then for each each k from I to j, we take dp of ik plus dp of kj.
dp of I comma k stores the smallest product from ai to ak, right? This is going to store aj from what? What
So
goes here?
ak plus 1.
Yes. So whatever that k is going to be, k is 1, 2, 3, 4, 5, whatever it happens to be. We want the minimum k. So we say the min k such that dp of ik, which is this product, plus this product. So this would be k plus 1, comma j.
In that case, then the k less than or equal to j needs to be strictly less than.
Yes.
You don't take a range of negative size.
Yes, thank you. K plus 1 can be at most j, so k must be strictly less than j, yes. One more thing, though, problem. There's a bug here, let's find it. Yeah,
Oh yeah, we also need to add the cost of that final outer multiplication.
exactly. Not only we have this subproblem stored for us, we have this subproblem stored for us. Not only do we take the min over all possible k, we need to consider the fact that it's this plus this recursively and the product to multiply these two together. So whatever that product is going to be the cost we need to consider. And that's going to be our cost function. So if it's going to be, the dimensions of the matrix will be the last ones left and the right ones right? So what is that, well, the cost we said is the product of those. So it's going to be what? Let us suppose that the matrices A1 through AN have dimensions D0, D1, D1, D2, and so on. And this is Dn minus 2, Dn minus 1, and this is Dn, right? If we zero index the dimensions but one index the matrices, let A1, for example, be dimension D0 times D1, and let's say AN be dimension Dn minus 1 times Dn, right? So for computing a subproblem in terms of I and j, we want the left dimension of AI and the right dimension of aj, and something about k. So what should our cost function be here?
D0 dn minus 1. I mean, D0 dk.
Well, we need I and j, so let's suppose it's AI.
Sorry, di, dk, dj.
Almost. We need the left one of, I'm saying, I should say rows and columns, but let's just call it the left one. We need the left one of di. I minus 1, just, it's not important, it's just a convention thing. Di minus 1 times what? AI to AK has dimensions, it's going to have the right dimension be k, and the right dimension of this one is going to be dk. J, excuse me. Right, let me just do that. So that is going to be the cost to do the final outer layer multiplication. And that's why we add that for each term, right? So we take the min over not just the cost of computing these subproblems, but the cost of computing those subproblems with the cost to combine. It may be the case that these are both small and then the cost to combine is really big. It might be the case that this is really small, but then these are really big, right? As long as we take the min over all of it, we're good. So this is the min over all possible, that's the answer, that's the QED. Yes?
Yeah, in your min there, you have 2 left parentheses and 1 right parenthesis.
Thank you very much. Here we go. Yes. Okay. Questions on the recurrence? We'll fill it in. We'll give an example. We'll illustrate how the recursiveness works. Base cases are what? I can think of a number smaller than 2.
1.
1? Okay. So what entries of our table get filled in? Yeah. Yeah. So for all I, we're going to set a dp of I comma I to be what? I comma I, and again, delegate to the English sentence. We want dp of ij to compute the min cost of computing ai to aj. So if we're doing ai to ai, What is the cost to compute AI to AI? Yeah, it's going to be 0. Also, that's another reason it's important we have this thing here, because if you think we didn't, we would take mins of zeros plus zeros, mins of zeros plus zeros plus zeros, and so on. The whole table would be zeros. So we definitely need something in there that's not a 0. So we got to have that. It's one reason that's necessary, besides the fact, if you didn't have that, the whole table would be zeros, right? Yes?
So what are we taking the min of? Because there's only one term in that min function.
For all possible k. As we fill in the thing, you'll see. So for example, it could be the min, it could be like min of our options would be, let's say dp of, let's say 1, 1 plus dp of 2, 3 plus something. Or it could be dp of 1, 2 plus dp of 3, 3 plus something, right? So in fact, if you think of the min like a for loop, the length of the for loop increases as I and j grow apart. That'll become illustrated as we do. We'll fill in a very rigorous example. We'll figure that out, but yes, it is O of n cubed. The analysis will take an extra sentence, though. Let's just do the code. Any questions on the recurrence, the correctness of the recurrence? Again, don't really care about this problem of chain matrix multiplication. The idea is this partition dp, where you consider all possible ways you could split something up at the top level, have that cost, and then recursively compute, with the recurrence, have the left and right parts, right? Let our input be d0 to, let's say, dn. So we have n plus entries. Dp of I comma j. Let's call this dp of, let's say, 1 to n, 1 to n, all zeros. For I in 1 to n, dp of I comma I is equal to 0. Now, when you just zero it out, you don't have to actually implement that step, because you computer-specific stuff doesn't really matter. This class, we need to say it out loud so we know what our base cases are. Were we to prove correctness, inductive hypotheses work as they are, you need a base case, right? Now we're going to do the crazy weird for loop where we loop over anti-diagonals, right? We need to first, when we have such a construction like this, which is also the case when we did longest palindromic subsequence, dp of ij contains subproblems I to j. But it can never be the case that j is less than I. J is at most equal to I. So in fact, this whole bottom table is not there. And we want to fill in the table in such a way that we go smaller and smaller diagonals. So we need to make sure we do the for loop in the correct way. So what we do is loop over the length, which is going to be for s in 1 to n, and then for I in 1 to n minus s, we set j equal to I plus s, and then call upon dp of ij to be equal to what we say it is, the min k, I less than equal to k less than j. Now, were you to actually implement this in a higher level program, taking the min of a variable number of objects would be better done with a loop. So just pretend it's a loop. dp I comma k plus dp of k plus 1 comma j plus di minus 1 dk dj. Okay? What element of the table do we return? Yeah.
1 comma n.
Correct. That's going to be matrix 1 to matrix n, so that's the answer that we want, right? Another thing with this S trick, if you think about it, let's suppose you didn't replace j as a function of I and s. dp of ij would then actually be what? dp of I and then I plus s, right? So s is increasing as well. It's the length of stuff. I make sure that I plus s does not exceed n. So this is just like a sliding window, if you think about it, of 1 comma 2, 2 comma 3, and so on. And then they're 2 apart, they're 3 apart, they're 4 apart, and so on. That's the way we're going to compute it. So this is the pseudocode for it. Not too difficult, actually, to look at. What's the runtime? Why? easy way to say, okay, 2 for loops, and then there's a min here that's also a loop of at most n. So this is n cubed. Can you do a more careful analysis? This is not a serious question. Can you do a more careful analysis and get a better answer? This is a double for loop, but notice you're only filling in half of the matrix. And as you increase, as this loop increases in length, the number of things that you're checking increases, but then the number of items that this min is computed for decreases. For example, there's one item here, but the min is at most over n objects. But there's only one cell that you fill this loop over, right? So that one grows while the other shrinks. The open-ended question is, does a more careful analysis lead you to a better upper bound?
Just a constant, because half the table is still just 1/2, which is a constant.
Yeah, half of n squared is still just n squared over 2, which is big O of n squared. And in fact, for the fact that one increases while the other decreases also doesn't really matter, because it's also true, for example, 1 plus 2 plus 3 plus n, as these increase instead of n plus n plus n plus n, right? N plus n plus n plus n plus n is just n squared, right? But does anyone know what 1 plus 2 plus 3 plus 4 plus whatever is up to n?
N times n plus 1 divided by 2.
Yes, Gauss as a baby figured that out, and that's just still O of n squared. Doesn't matter. So no, a more careful analysis will get you, it might get you constants, but it won't get you anything better. Question?
What did you put as the parameters for CMM?
Those are the dimensions of the matrices where D0 to Dn are integers given to us, such that D0, D1 consists of the pair of dimensions for A0, A1. D1, D2 consists of the dimensions for A2, and so on. The dimensions of An are Dn minus 1 and Dn, right? So for example, in this specific for this specific problem, the array, the dimension of that would be given to us would be 50, 20, 1, 10, 100. That would be our input. And we would know that this is A, we would know that this is B, we would know that this is C, and we would know that this is D. Questions? All right, let's do a quick example. We have 5 elements in our input, so we're going to have 4 by 4 table. Note that this whole part is zeroed out. Right? Don't really care about that. The diagonal is going to be filled with our base cases, which are going to be 0, 0, 0, and then 0. What is the I and j for this cell? Yeah, so we want to compute dp of 1, 2 first, right? The way the for loop with that s is going to work, it's going to go this one, this one, this one, this one, this one, and then this one. It's going to go through these diagonals, right? dp of 1, 2, according to our thing, should be the min k, which is less than or equal to 1 and strictly less than 2 of dp of I comma k, I comma k plus dp of k plus 1 comma j plus di minus 1 dk dj, right? But observe that this loop only goes over one thing. So the min is over one thing. That is simply going to be dp of, 1 comma 2, 1 comma 1, thank you, plus dp of 2, 2, thank you, plus the cost of those matrices, which is, let's do it for this specific one, it's going to be, A is going to be 50 by 20, and then this is going to be 20 by 1, so it's 50 by 20 by 1. Right? double check me, I'm not making any mistakes here. Again, we want to compute dp of 1 comma 2. And what is that supposed to correspond to? That's supposed to correspond to AB for us. So the min cost to compute AB is of course just going to be the cost to compute AB. What is dp of 1 comma 1? What is dp of 2 comma 2? What is 20 times 50 times 1? So this is going to be 1,000. Okay. Similarly, dp of 2 comma 3, we can skip a little ahead and know we're going to take the min of two other things and the cost to compute that, which is going to be what? We want to compute 2, 3. So we want to compute b times c. So it's going to be 20 times 1 times 100, which is going to be what? What's 20 times 1 times 100? Times 10? Sorry, 200, I'm sorry. 20 times 1 times 10 is 200. And dp of 3 comma 4 is going to be, this is supposed to represent, let's see, 3 comma 4 is supposed to represent c times d, right? And what is c times d going to give us? 1 times 10 times 100 is 1,000. Let me just double check myself. Yeah, okay. All right, so now we need to do dp of the next, this one. What is this one's entry? 1, 3. And we know that's going to be the min of two things. This is going to be dp of 1 comma 1 plus dp of 2 comma 3 plus what is the dimensions here? It's going to be 50 times 20 times 10, right? Then we take the second option we take the min of is dp of 1 comma 2 plus dp of 3 comma 3, which is going to be dp of 1 comma 2 is going to be dimension-wise is going to be 50 times 1 times 10, right? Now again, what are we really taking the min of? What do these two options correspond to? This one corresponds to 1 comma 1 and 2 comma 3 is A, then BC, and then this one is AB, then C, right? So to compute ABC, these are the two options. We're taking the min of both of those. But we already computed BC and AB in the table. So this is A, this is BC, that's AB, and that's C. So that's what's going to happen. And what is this? That's 0. That one's 0, that one's 0. So what is dp of 2 comma 3? We go to here, that's 200. So this is going to be the min of 200 plus, what's 50 times 20 times 10? What? It's 1,000. I'm not doing the math. Someone do the math? 10,000, that sounds right. And then what's, that's going to be 1, 2 is going to be this one, so that's 1,000, excuse me, plus 50 times 1 times 10, 500. Okay. 10,000, 1,500, we're going to take the 1,500. We're taking the min. So this one is 1,500, right? And in fact, I'll write out where this min came from. dp of, what is this, 1 comma 3. We did, notice that we chose this second one as part of the min. So to compute ABC, it is cheaper to do AB then C than to do BC then A. So we want to do AB and then do C if we wanted to compute ABC. So this one corresponds to AB then C, right? I also want to illustrate where in the table does this occur, right? So dp of 1 comma 1 is here, and dp of 2 comma 3 is here, right? So one of them is always going to be in the column, and the other is always going to be in the row. Now when you consider the other option, it's this one. So you're considering these two plus your cost versus these two plus your cost. That's going to be how the recurrence works. One of them is going to slide over the row, and the other is going to slide over the column. Right? You guys see it? So this one specifically references AB, which is that one, and then C, which is that one, right? So that's the one it chose. Let's do another. Let's do dp of, do dp of, this one is going to be 2, 4. So that's going to be the min of two options. Min of, our two options are dp of 2, 2 plus dp of 3, 4 plus the cost of this, which is going to be 20 times 1 times 100. Thank you very much. This one is going to be dp of 2, 3 plus dp of 4, 4, which is going to be plus 20 times 10 times 100, right? That's going to be 0, and that's going to be 0. So this is going to be the min of 3, 4. We're looking at this value. So we're actually going to compare these two cells with the cost, and then these two cells with the cost. So what is dp of 3, 4? That's going to be 1,000 plus, what is that, 2,000? Then we're going to compare dp of 2, 3 is going to be 200 plus 20 times 10 times 100 is, what is that, 10,000, 20,000? Double check me. Sounds right. That's 3,000, that's 20,200. So we're going to take the 3,000 option, right? So this one is going to be 3,000. And that's dp of 2, 4. And that computes for us BCD, but in what association? We chose the 200 one, so it's going to be BC then D, right? So that's the cheapest way to compute BCD, is to do BC then D, right? Finally, we have one left here. We want to compute our final answer, which is dp of 1, 4. So we're going to take the min over three things. We're going to take the min over, and just to illustrate this, this corresponds to, had we done A, then BCD, had we done AB, then CD, or had we done ABC, then D. And those are all going to be computed as part of subproblems. So we're going to take the min of those three options. ABCD is going to be, this is going to be dp of 1, 1 plus dp of 2, 4 plus, what are the dimensions of that? That's going to be 50 times 20 times 100. This is going to be dp of 1, 2 plus dp of 3, 4, which is going to give us 50 times 1 times 100. This is going to be dp of 1, 3 plus dp of 4, 4 plus 50 times 10 times 100. Right? Please double check me, I'm not making any mistakes. And let's just fill those out again. That's going to give us 0 plus, what's dp of 2, 4? 3,000 plus, what's 50 times 20 times 100? 100,000, okay? What is, that's too big. What's dp of 1, 2? 1,000 plus dp of 3, 4 is 1,000. What's 50 times 1 times 100? 5,000. What's dp of 1, 3? 1,500. What's dp of 4, 4? It's going to be 0. And then what's 50 times 100 times 10? 50,000, yeah. Okay, so the min is, this is like 103,000, this is like 51,000, this is like 7,000, right? So that's, in fact, that is exactly 7,000. So that is going to go here. By the way, 7,000 was the answer we computed at the end, right? Excuse me, at the beginning. And notice that which one you took the min of is exactly corresponding to the last multiplication required. Then each of these is handled recursively, right? So in fact, what this means is that this 7,000 references the costs to do BC and, the cost to do CD, and then the cost to do AB, right? So it computes, it checks this one, and this one, and it takes the min of these three options with the cost function, and it decides this one is the cheapest. Doing AB, then CD, then ABCD is the cheapest way to do it, right? Which one you take the min of is, in fact, exactly how the parentheticalization works. This is the classic example of a partition DP, right? It works in a non-monotonic way, and the subproblems, all the possible subproblems basically have to be stored and computed for us, right? Again, if you think about this as composing two trees to make a larger tree, you need to know all possible combinations because you need to choose as one grows, the other shrinks, and so on, right? Notice as this first product gets bigger, A to AB to ABC, the second product gets smaller. It's BCD to CD to D, right? So you need all possible combinations of that, it turns out, the min of those, and then you DP it up. Question? Yes.
Basically, instead of allowing us to skip calculations, in this case, DP just ensures that we don't repeat calculations that we don't need to.
A naive view of DP is that if you do it recursively, you just store subproblems and then call upon those in the Fibonacci sense. But this is an example, I think, that's a little non-trivial because you need to know which subproblems to store efficiently. And you need to know to store them in the correct order. That is a bit non-trivial. And to know that you can go kind of to take the min over all these possible options, I think requires a little bit more than saying storing the subproblem, because you kind of got to know how to store them and which way the next one is computed. So it's a little bit more than that, it turns out. I mean, not really, but kind of, right? What else can we say? Again, this is not a technique that applies every single day, and sometimes I've thought about removing this lecture, and then one time we had a guy who said, thank you for showing chain matrix in class because it was on my interview like the next day. So then that means I can never remove it from the thing. It's a naive technique. I mean, it's not naive, but it's not extremely common. But when it does apply, it's like the only thing that works. You can apply such problems that require any kind of association like this. There are problems that involve binary trees and operations that do this. And not only is it the way that you partition the problem and solve those with DP, but also the way that you fill in the table, right, in such an upper triangular matrix. Final questions? All right, let's take a break.